Penguin Random House Audio presents Through Two Doors at Once, the elegant experiment that captures the enigma of our quantum reality, by Anil Ananthaswamy. Read for you by René Ruiz. Allow me to express now, once and for all, my deep respect for the work of the experimenter, and for his fight to wring significant facts from an inflexible nature, which says so distinctly no and so indistinctly yes to our theories. Hermann Weyl, German mathematician, 1885 to 1955. Prologue. The story of nature taunting us. The office is simply the most uncluttered of any physicist's office I have ever seen. There's a chair alongside a small table with nothing on it. No books, no papers, no lamp, no computer, nothing. A sofa graces the office. Large windows overlook a small lake, the trees around which are bare, except for a few stragglers that are holding on to their fall foliage, defying the approaching winter in this part of Ontario, Canada. Lucien Hardy puts his laptop on the table, pointing out that he does most of his work in cafes, and figures that all he needs in his office is a cafe-like small table to set down his laptop. There is the obligatory blackboard, taking up most of one wall of his office. It doesn't take long for Hardy to spring up and start chalking it up with diagrams and equations, something that most of the quantum physicists I meet seem inclined to do. We start talking about some esoteric aspect of quantum physics when he stops and says, "I started off the wrong way." To reset our discussion, he says, "Imagine you have a factory and they make bombs." He has my attention. He writes two names on the blackboard, Elitzer and Weidmann. He is talking about something called the Elitzer-Weidmann bomb puzzle. Named after two Israeli physicists, the puzzle exemplifies the counterintuitive nature of the quantum world in ways that non-physicists can appreciate. It confounds physicists too in no small measure. The problem goes something like this. There's a factory that makes bombs equipped with triggers. The triggers are so sensitive that a single particle, any particle, even a particle of light, can set them off. There's a big dilemma, however. The factory's assembly line is faulty. It's churning out both good bombs with triggers and bad bombs without triggers. Hardy writes them as good and bad and quips about the quotation marks. Obviously, you may have a different moral perspective on it. The task is to identify the good bombs. This means having to check whether the bombs have triggers. But examining each bomb isn't the correct strategy, because in order to do so, you'd need to shine light on it, however faint, and that would cause a good bomb to explode. The only ones left unexploded would be the duds without triggers. So, how does one solve this problem? If it helps, we are allowed one concession. We can detonate some bombs, as long as we are left with some good undetonated bombs. From our everyday experience of how the world works, this is an impossible problem to solve. But the quantum world, the world of very small things like molecules and atoms and electrons and protons and photons, behaves in bizarre ways. The physics that governs the behavior of this microscopic world is called quantum physics or quantum mechanics. And we can use quantum physics to find good bombs without setting them off. Even with a simple setup, it's possible to salvage about half the good bombs. It involves using a modern variation of a 200-year-old experiment. Called the double-slit experiment, it was first done in the early 1800s to challenge Isaac Newton's ideas about the nature of light. The experiment took center stage again in the early 20th century when two of the founders of quantum physics, Albert Einstein and Niels Bohr, grappled with its revelations about the nature of reality. In the 1960s, Richard Feynman extolled its virtues, saying that the double-slit experiment contained all of the mysteries of the quantum world. A simpler and more elegant experiment would be hard to find, the workings of which a high school student can grasp, yet profound enough in its implications to bewilder brains like Einstein's and Bohr's, a confusion that continues to this day. This is the story of quantum mechanics from the perspective of one classic experiment, and its subtle, sophisticated variations, including one that, as we'll see, solves the Elitzer-Weidman bomb puzzle. Whether these variations are carried out as thought experiments by luminous minds or painstakingly performed in the basement labs of physics departments. It's the story of nature taunting us. Catch me if you can. Chapter 1. The Case of the Experiment with Two Holes. Richard Feynman explains the central mystery. There is nothing more surreal, nothing more abstract than reality. Giorgio Morandi. Richard Feynman was still a year away from winning his Nobel Prize, and 2 decades away from publishing an endearing autobiographical book that introduced him to non-physicists as a straight-talking scientist interested in everything from cracking safes to playing drums. But in November 1964, to students at Cornell University in Ithaca, New York, he was already a star, and they received him as such. Feynman came to deliver a series of lectures. Strains of Far Above Cayuga's Waters rang out from the Cornell chimes. The provost introduced Feynman as an instructor and physicist par excellence, but also, of course, as an accomplished bongo drummer. Feynman strode onto the stage to the kind of applause reserved for performing artists and opened his lecture with this observation. It's odd, but in the infrequent occasions when I have been called upon in a formal place to play the bongo drums, the introducer never seems to find it necessary to mention that I also do theoretical physics. By his 6th lecture, Feynman dispensed with any preamble, even a token hello to the clapping students, and jumped straight into how our intuition, which is suited to dealing with everyday things that we can see and hear and touch, fails when it comes to understanding nature at very small scales. And often, he said, it's experiments that challenge our intuitive view of the world. Then we see unexpected things, said Feynman. We see things that are very far from what we could have imagined. And so our imagination is stretched to the utmost, not as in fiction, to imagine things which aren't really there, but our imagination is stretched to the utmost just to comprehend those things which are there. And it's this kind of a situation that I want to talk about. The lecture was about quantum mechanics, the physics of the very small things. In particular, it was about the nature of light and subatomic bits of matter such as electrons. In other words, it was about the nature of reality. Do light and electrons show wave-like behavior like water does? Or do they act like particles, like grains of sand do? Turns out that saying yes or no would be both correct and incorrect. Any attempt to visualize the behavior of the microscopic, subatomic entities makes a mockery of our intuition. They behave in their own inimitable way, said Feynman, which technically could be called the quantum mechanical way. They behave in a way that is like nothing you have ever seen before. Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different. They do not behave just like particles. They do not behave just like waves. But at least light and electrons behave in exactly the same way, said Feynman. That is, they're both screwy. Feynman cautioned the audience that the lecture was going to be difficult because it would challenge their widely held views about how nature works. But the difficulty, really, is psychological and exists in the perpetual torment that results from your saying to yourself, "But how can it be like that?" Which really is a reflection of an uncontrolled, but I say utterly vain, desire to see it in terms of some analogy with something familiar. I will not...
Sample complete. Ready to continue?